Hi everyone. This video will present the chain of operations performed on a given original matrix to produce the inverse matrix. We'll briefly go through the overall process, then punch down into the details of each step in the chain. We're looking to achieve an intermediate goal of creating an inverse matrix. Our ultimate end goal is using that inverse matrix to solve systems of equations, but this video will focus on the steps involved in calculating the inverse matrix. We'll do that by creating a series of matrices in a processing chain that starts with the matrix we want to find the inverse of. We call that the original matrix. From this original matrix, we will calculate a minor matrix. We will slightly modify that minor matrix to produce the cofactor matrix. We'll further modify that cofactor matrix to produce the adjugate matrix. And finally, we will adjust the adjugate matrix to give us the inverse matrix. Let's get into the details of it all. The minor matrix is created by replacing each element of the original matrix with the determinant of the matrix that remains when the row and column of the original matrix that contain that element are eliminated from the original matrix. Let's go through an example. Number 8 shows a 3 by 3 matrix. This is our original matrix. This means our minor will also be a 3 by 3 matrix. We're going to work through each element. We'll start with the first one. We eliminate the column, the row, and we work with the determinant that's left. That completes the 3 by 3 minor matrix. Let's go through an example of a 2 by 2 minor matrix. This will be substantially easier than the 3 by 3. We know, because we start with a 2 by 2, that we're going to be left with a 2 by 2, and we follow the same process. We replace each element with the determinant of the remaining matrix when we eliminate the column and row of the element we're looking to replace. So we eliminate those two, but we're left with something that isn't really a determinant, so we just drop that value in. And that completes the 2 by 2. The cofactor matrix selectively changes the sign of specific elements in the minor matrix based on the position of the element. Each element is identified by a subscript indicating its row and column. We add the row index to the column index for each element. If that result is odd, we flip the sign of the element. If that result is even, we leave the sign alone. So as we go through this particular matrix, we see we have A11, but when we add those values together, we get 2, which is even. A11 stays the same. For A12, this is, when we add those values together, this becomes odd. The cofactor takes on a negative sign for A12. When we add 1, 3 together, we get 4. That stays the same. Adding 2, 1 together, we get 3. This changes sign. A22, when we add those subscripts together, this becomes even, 4. That remains the same. A23, we add those together, we get 5. This is minus. Adding A31 together, we get 4, which is even, so that remains the same. A32, when we add 3 to 2, we get 5. That becomes odd, so this takes on a negative value. And for 3, 3, we get a positive value. Adding those together turns out to be an even number. This pattern repeats itself, and we see this with 2 by 2s, 4 by 4s, 5 by 5s. We follow the same process. This just means that we multiply each element in the minor matrix by +1, -1, +1, -1, +1, -1, +1, -1, +1 for a 3 by 3. If we had a 2 by 2, that pattern still repeats itself. We would get a plus, minus, and a minus. Oops. And a minus, plus. Let's go through an example of finding the cofactor matrix for a given minor matrix. We know that we have a certain sign modification scheme where we add the subscripts of the elements together, and if this is odd, we flip the sign, and if it's even, we leave it alone. So I'm just going to identify the elements in this particular matrix that are going to have their signs flipped. Once we've done that, we're going to produce a same 3 by 3 matrix. And the only difference between the minor matrix and the cofactor matrix is the sign of those elements that is adjusted. Let's go through an example with a 2 by 2. We know we're going to end up with a 2 by 2 matrix, so we'll just leave that as it is, and we'll identify those values that are going to have their sign flipped. We just go through the matrix and change those signs, so we have -8, -5, +9, and +5. In order to talk about the adjugate matrix, we need to introduce a new operation that we call the transpose. We can take the transpose of a matrix by swapping particular elements. And a transpose is defined as creating a new matrix. In fact, we'll call this new matrix A, which is equal to C transpose. And we indicate that it's the transpose by having that superscript T above the original matrix. This matrix C is this same matrix here with these elements shown. And we create the transpose by defining the row and column A sub ij of the new matrix, the transpose of that, as being the element that occurs at Cji. So we're just swapping row with column for each one of these things. Now we can see that along our diagonal that the row element and the column element are equal. This means that if for our new matrix, A, which will equal C transpose, our diagonal elements are going to be exactly the same. So this becomes C11, C22, and C33. But now we wind up with these other elements, and we can see that 2,1 and 1,2 are opposite. We actually wind up flipping these values or mirroring them over the diagonal. So if we have C21, this is going to become, in our transpose, C21 actually gets placed in the 1,2 position. And C12 gets placed here. This is also true for the other elements, and we have C31 and 1,3, so we're going to swap those. And finally, we have 3,2 and 2,3. And this particular operation is used in more than just finding an adjugate, but we'll continue on with some examples of how this is going to work as we move into calculating the adjugate matrix given a cofactor matrix. And this is the next step in our chain. Let's look at a 3 by 3 example. And to calculate the adjugate, we know that we're going to get a 3 by 3 on the output of this operation. And we also know that the adjugate matrix is equal to the transpose of the cofactor matrix. So all we're going to do is swap elements in this to find our new matrix. We're going to look at our diagonal, and that is going to be exactly the same in our adjugate matrix. So we'll just fill that in first. 4, -2, -1. And now we're going to swap elements across that diagonal. So we're going to replace 1 and -1 here. to replace -4 and -1. And finally, we're going to replace, oops, we're going to replace -1 and -5. This is just a swapping of elements across the diagonal, and the diagonal remains the same. For a 2x2 matrix, we wind up with similar operation. We know we're going to get a 2x2 on the output of this, and we know that our adjugate matrix is going to be the transpose of our cofactor matrix, and we're given the cofactor matrix here. We're going to identify our diagonal and just drop that in directly, and we are going to swap elements. This isn't a very good example. We're going to swap elements across this. Let's do number 25 as well here, so that this is a little more obvious. So we're going to get a 2x2 matrix, and again, this is given the cofactor matrix. So we identify our diagonal, we drop that in, and then we're going to swap our elements. This is 2, 1, and this is 1, 2. So we're going to transpose that by swapping them, and this becomes, whoops, this becomes 6, and this becomes 7. And this is the adjugate matrix. And we'll finish off with one long example that starts with the original matrix and ends with the adjugate matrix. So this means we're going to need to find the minor, which is the major amount of work in the overall process. Then we find the cofactor matrix, and finally the adjugate. So let's step through with number 11 and find the minor matrix first, and I'll label that as M. And we'll make this kind of big. And we'll just cycle through the same way we did this before. So we've completed the 3x3 minor matrix. Our next step is to determine the cofactor matrix, but we know that the cofactor matrix is the same thing as the minor matrix with selectively modified signs to certain elements, and I know that that is plus, this gets flipped, this is flipped, this is flipped, and this is flipped. So my cofactor matrix C will be equal to, and I'll draw this one a little bit smaller, -8 plus 8 minus 24, 0, 0, 4, 6 minus 4 minus 18, oh sorry, plus 18, and finally we will find the adjugate matrix, and I'll slide down a little bit so that we can do that kind of cleanly here. And we know that to find the adjugate, we're finding the transpose of the cofactor matrix. So the first thing I need to do is identify my diagonal, which is here, and I keep that. And now I'm just going to swap values across the diagonal. So I'm swapping the 0 and the 8. And I'll be swapping the 6 and the minus 24. And finally swapping the minus 4 with the plus 4. And it's complete. In our next video, we'll take a look at finding the inverse from the adjugate, which is just one step further, but that'll be all for now. Thanks for watching.